Hi, this is Nishant, and our topic is visualization of Java program execution. And coming to the introduction, GIV, which is real world open source visualization system that supports object diagram and the sequence diagram runtime visualization of Java programs. These object diagrams are very much related to UML diagrams that are used for specific design type decisions. We have been developing the state-of-art visualization, debugging, and the dynamic analysis system of Java programs. An object diagram captures the current state of execution in terms of active objects and their interconnection, whereas the sequence diagram captures the history and the method of interactions between the objects. The main contributions: vertical compaction of the sequence of method navigation using the regular expression labels and an OAuth2 algorithm for computing labels. Horizontal compaction of object lifelines, supporting both the elimination of object lifelines as well as grouping lifelines together. The introduction of execution filters to allow the user to remove interactions that are not of interest, referred to as out of model calls. Extension of aforementioned techniques for multi-threaded programs and an introduction of new notations for a compact representation of the thread interactions that are overlapping and possibly interfering with one another. Coming to JIV architecture, JIV is adaptable for many number of applications, and it is also traditional debugger to sustains the features. JIV Java program is a debug mode, and these events are composed into an in-memory model. These events are collected into an in-memory model. Derived models are constructed in order to support the dynamic visualizations. In some aspects, JIV resembles to traditional debuggers, allowing one to define breakpoints, inspect variables, step into and over the instructions, and so on. Coming to JIV architecture, this is a brief JIV architecture where the upper part shows the JIV user interface and the debugger user interface, where it shows the JIV data models, JIV controllers, and JPD debuggers. Where the JIV data model contains the trace model, object model, and sequence model. Coming to the controller, JIV controller contains the event handler, model manager, and UI engine. And coming to JID event JPDA debugger, it contains the front end, back end, and debug JVM. And in this we can see the brief description of the JIV architecture. Coming to the events supported by JPDA, there are many events supported by JPDA. There are like virtual machine start, death, and disconnection, class prepare and unload, thread start and death, method call and return, field access and modification, exemption throw and caught line set, call trees and vertical compact. Call trees are the basic structures that catch the hierarchy caller Kali connection for the procedural program execution. At the execution time, the call tree develops in a profundity first way. When execution has achieved a specific hub, all the hubs on the way from the base of the tree to this hub speak to the heap of the remarkable strategy calls. The grouping graph can be seen as a call tree that is shown in a flat left to right way. Aside from the protest lifesavers are caught in the customary call tree. When the compaction and the encoding operation are applied on the call tree, the resulting tree will have two types of nodes, ordinary node as well as the new type of node, that is a compact node. The maximally compacted tree is one that is obtained by repeated applications of compaction and encoding operations on the call tree in the bottom up, left to right and order until the tandem repeats sequence are left in the tree. A maximally compacted tree can be expanded to an ordinary call tree by repeated application of the expansion and decoding operations in the top down, right to left order until the compact nodes remain. Coming to horizontal compaction, the simplest case of horizontal compaction during vertical compaction arises when a method makes nested call to methods in other objects. After compaction, the set of insertions will be replaced by single call insert, hiding the underlying transversals for each of the n-insert operations. Grouping can be in a significant reduction of sequence diagram size when multiple objects of class are present. Choosing the representative object of each class is sufficient for conveying the intended effect. The benefit being that the horizontal spread of the sequence diagram is minimized. Multi-threaded execution compaction. In multi-threaded environment, control may shift between the threads in an unpredictable manner during the course of execution. While the call made by the thread may remain the same, the interleaving pattern may vary between the two executions depending upon the synchronization primitives used. In all the scenarios, the call sequence by the three threads, when considered individually, remains the same. That is, the main instantaneous buffer producer executes to write operations and consumer executes to read operations. The write and the read calls made by the producer and the consumer threads respectively are interleaved. The manner in which write and read calls are interleaved are different. The non-overlapping scenario denotes the facts that there is no interleaving really between the producer and the consumer threads. Every node in multi-threaded call tree represents a method call, where the method call on the object, M on the object, and O in the thread, T as S and E are the calls start and the return event numbers respectively. In the presence of more than two overlapping cables, multiple types of interleaving are possible between every pair of threads. Coming to the advantages of JIVE, JIVE takes a higher level view and vertical compaction and aims to construct a minimal regular expressions labels that can consistently represent the sequence of method calls. JIVE's compaction is semantically rather in that it reduces the diagram and provides an intuitive and concise description of hidden substructures. JIVE also caters the horizontal compaction and the ability to draw the sequence diagram even when there is a missing calls which have been abstracted away because of various filtering techniques. The encoded schemes adopted by JIVE allows one to expand the compacted diagrams in a step-by-step fashion. Conclusion: the use of object and sequence diagram can give clear and intuitive visualization of object-oriented program execution. Current state of execution can be captured by using the object diagram, while the interaction between the objects and the particular input data can be summarized by the sequence diagram. These charts were initially proposed for the use of the configuration time in the UML, yet we have to adjust the documentation for the use at the runtime and have consolidated them as the future of functional representation framework for Java called JIVE. And this is the end of the session. Thank you so much.